Bismillahirrahmanirrahim. Uh, so today we will start with our fourth lecture, and the topic of our today's lecture will be the introduction to the quantum mechanics. For this lecture, we will follow the book Semiconductor Physics, written by Neyman. So we have learned this chapter in our fourth semester. That one was semiconductor devices, and and also I was your teacher on that course. So what actually we will do, we will just recap our previous knowledge and try to understand if we have any problem there. Now, so first of all, the name is quantum mechanics. So what is quantum mechanics and what is classical mechanics? What is the difference between the quantum mechanics and the classical mechanics? So before starting in details of quantum mechanics, first of all, I would like to tell you what is classical mechanics. The classical mechanics, or this one is also known as Newtonian mechanics. In case of Newtonian mechanics, we know there are three formulas. The first law is if an object is in a static positions, then that one will be static, or if object is in motion, then that one will be motion up to infinite time. Next, second law was F equals to ma. The rate of change of momentum is proportional to the force, and the last formula is to every actions there is an equal and opposite reaction force. So look, in case of Newtonian mechanics, most of the things are uh, actually depends on time. But in case of quantum mechanics, that one actually deals with the uh, nanoparticles level. That means the electrons or the lattice structure of the materials and so on. So if you go through the first part, then you will also understand that there will be in the second para you learn that the motion of the large object such as planet and satellite can be predicted to be an high accuracy, to high degree of accuracy using classical theory of physics. So what is classical physics? Classical physics means the Newtonian physics, and but in case of electrons and high frequency electromagnetic wave, we cannot describe in details about their using our classical physics. So for this reason, quantum mechanics is it actually deals with the wave theory and also the theory of the semiconductor physics. Now, we'll start from the article number 2.1, the principle of quantum mechanics. Look, before starting the quantum mechanics, we need to understand three basic principles of quantum mechanics. The first principle is principle of energy quanta. Second one is wave particle duality principle, and third one is the uncertainty principle. In our today's lecture, we actually go through these three topics. Okay. So first of all, article number 2.1.1, that one is energy quanta. So what is called energy quanta? So for in different experiments, it shows that whenever we know about the photoelectric effect, right? That one is the if monochromatic light is incident on a clear surface of a material, then under certain conditions the electrons are emitted from the surface, and that one is the photoelectric effect. Say for example, if we have this surface, and that means if we if a monochromatic light falls on this surface, that means after a certain conditions, the electron will move or electron will emit from this surface. Okay, so that one is the photoelectric effect. Now how does actually it works? Look, so we know these things. So whenever a monochromatic light falls on this surface, it that means at the surface, sorry, on the surface we have some free electrons. So it requires some energy. It requires some energy to remove this electron from the surface, or to shift this electron from the surface. So the maximum amount of energy, the minimum amount of energy that required to remove the or shift this electron from the surface is known as work function. Okay, so these things is described by the Planck postulates. These things is described by Planck's postulates in 1900. In 1900, the thermal radiation is emitted from a heated surface is discrete packets of energy. The thermal radiation is emitted from a heated surface is in discrete packet of energy, and this packet of energy is known as quanta. So whenever this light falls, monochromatic light falls, it generates some heat. So this thermal radiation is emitted from the heated surface. That means from this surface in discrete packets of energy. That means some energy will release from this surface, and this energy is known as quanta. So if in your exam this question comes, what is called quanta? So I think all of you should sorry, all of you should answer this thing. The next one is the energy of this quanta is given by E equals to h nu. This symbol is known as nu, where nu is the frequency of the radiations, and h is the Planck's constant. You know about the Planck's constant, as because this postulate is given by Planck, so this one is known as Planck's constant, and that one is denoted by symbol h. So h equals to 6.625 into 10 to the minus 34 joule seconds. Now, uh, in 1905, Einstein also interpreted the photoelectric effect by the suggestion of this energy, of these packets of energy. So if you look at this figure, if we look at this figure, 2.1, so this one is the material, and an incident monochromatic light, that one falls on the surface, and photokinetic energy T. The photokinetic energy is defined by T. So this amount of energy is released from this surface due to this monochromatic light. Okay, so this phenomena is known as photoelectric effect, and that formula, that energy E equals to h, and that one is known as nu. Okay, and this one is the frequency. Now, so I have already discussed these things. The maximum kinetic energy of the photoelectron, T max. So T max can be written equals to half mv square. So m is the mass of this electron, v is the velocity of that electron, h nu minus h nu naught. So this nu naught, this one is known as work function. This nu naught is known as work function. So work function means the minimum amount of energy. Work function means the minimum amount of energy that requires to release that electron from the surface. So this one is very important. What is called work functions. So is that clear? So this new value must be greater than this nu naught, because nu naught or h nu naught is the minimum amount of energy that requires to release that electron, and this one is known as work function. So there are a few maths, you know how to solve this math. The first question is to calculate the photon energy. That means you need to calculate the energy of a particular wavelength. The lambda value is given. So we know that E equals to h nu. So we know that frequency f or nu equals to c divided by lambda. We know the velocity of the light is constant. That one is 3 into 10 to the power 8. 3 into 10 to the power 8 meter per second. As because that one is given in centimeter, we can write 10 to the power 10, or you can convert this lambda value from centimeter to meter. I think this one is easier. Now, whenever we calculate the photon energy, we usually express this photon energy in terms of electron volt. So, how to measure this electron volt? Whenever you find the energy equals to 2.81 into 10 to the minus 15, if you divide this value by 1.6 into 10 to the power minus 19, so that one will give you the photon energy. Sorry, that one will give you the electron volt unit. Okay, so try to solve these things and related problems like this. Now move to the second topic. That one is wave particle duality. So the in this case we will define that the light wave can be explained in terms of wave and also in terms of particle. So in 1924, de Broglie, one of the scientists named de Broglie, postulates that the matter existence of matter waves. He suggested that since the wave exhibits the particle-like behavior, that means the wave shows the particle-like behavior. So expect that this particle also should behave like an wave. That means that vice versa. If something, if an wave-like things is described by a particle, so this particle should also be explained by the wave. So this postulate is known as wave particles duality. Now, this de Broglie's wave particles duality in de Broglie's wave particles duality, the momentum of the photon, the momentum is defined as p h divided by lambda. The momentum of this photon can be explained, and this one is the de Broglie's formula. Where this one is not a, this one should be lambda. This lambda is the wavelength. So similarly, the hypothesis is this wavelength can be expressed by h divided by p. Okay, and where this lambda is known as de Broglie's wavelength of the matter. I think this one is clear. So in this figure, they just show how de Broglie's wavelength is explained. So this one is the this figure is the experimental arrangement for the Davison's-Gemers experiment. So I am not going in details of these experiments. So just de Broglie's postulates or the wave particles duality postulates is that the moment of the photon p should be equals to h divided by lambda, or lambda should be equals to h divided by p, and this lambda is known as wavelength or de Broglie's wavelength. Okay. Now using these postulates, there are few formulas are there. So this one you will find this thing in example 2.2. Calculate the de Broglie's wavelength. That means you need to find out the lambda value, and the electron velocity is given. So you know the mass of the electron is 9.11 into 10 to the power minus 31, and this velocity is given in 10 to the power 7 centimeter per second. So we have to convert from this centimeter to meter. So this one is the momentum. After that, lambda equals to h divided by momentum. So you will get this wavelength value. So similarly, in whenever we will try to find out the lambda value or this wavelength value, then we have to express this wavelength in terms of angstrom. So that one should be equals to 10 to the power minus 10. 1 angstrom should be equals to 10 to the power minus 10 meter, or 10 to the power minus 8 centimeter. So try to solve these practice problems. Now article number 2.1.3. That one is very important. That one is uncertainty principle. or sometimes that one is known as Heisenberg uncertainty principle. So there is a very good relationships between the quantum mechanics and this uncertainty principle. So the first statement of the uncertainty principle is that this is impossible. It is impossible to simultaneously describe the absolute accuracy of the positions and the momentum of a particle. So if the uncertainty in the momentum is delta p, if the uncertainty of the electron is expressed in terms of delta, momentum is expressed in terms of delta p, the uncertainty position is delta x, then the first postulates or the first statement of Heisenberg was delta p multiplied with delta x should be greater than or equals to h bar. So this H, or this one is sometimes known as H naught. So this H naught is defined as H minus twice pi, and this one is known as modified Planck's constant, and this one is generally include the angular positions and also the angular momentum, as because this one is for the linear momentum and the linear positions, so same things can be described as angular momentum and also for the angular positions. The second statement is that the second statement of the Heisenberg uncertainty principle is that it is impossible to simultaneously describe the absolute accuracy of energy of a particle and instant of that time of the particle of this energy. That means this is impossible to find out the absolute accuracy of energy and also the instant of time the particle has this energy, that means that absolute energy. To find out this is impossible to find out that instant of time uh, at which this particle uh, has got this energy. So similarly, if we explain this uncertainty of the energy is described by delta E, and if the uncertainty of the time is described by delta T, so same formula will be delta E multiplied with delta T should be greater than or equals to H naught. Okay, so these two are known as the uncertainty principle. Okay, so using these two formulas, you will have to solve these practice problems. Now, one of the most important thing is that, so one consequence of the uncertainty principle is that we cannot, for example, determine the exact position of an electron. We cannot find out the exact positions of an electron. We will instead determine the probability of finding that electrons. So in our semiconductor physics, we learn about the probability density functions, or probability of finding the electrons, or probability of finding the holes, this sort of thing. So we cannot find out the exact positions of the electrons, but we can find out the, or we can assume the probability of finding that electron at that particular positions. Okay. So this one will be the end of the three postulates. So just recap this total things. So in this article 2.1, what actually we learned. So if we move to the first one, so in this chapter there are three principles. So in case of quantum mechanics, before going in details of quantum mechanics, we need to know three principles. So first principle is energy quanta. Next one is the wave particle duality principle, and the last one is the uncertainty principle. So these are the three postulates. So similarly, similar to the Newtonian physics, there are three postulates. That one is the, if a body is static, that one will be static for infinite period of time. If that one is in motions, that one will be in motions for infinite period of time. Second law was F equals to ma. Third law is equals to every action state has equal and opposite reaction. So these are the hypotheses, or these are the principles. So based on this principle, so we describe most of the formulas of Newtonian physics. So similarly, in case of quantum mechanics, we have to follow few principles. The first principle was energy quanta. So what was energy quanta? We have described the energy quanta as E equals to H. Sorry. So we need using the photoelectric effect, we describe this energy quanta. That one is P max. That means the maximum kinetic energy equals to half mv square equals to h nu minus h nu naught, where h nu naught is known as work function. And the second one was the wave particle duality. So in this case, we explain the momentum. If the momentum is p equals to h divided by lambda, and this one is described by de Broglie. And the third one was the uncertainty principle. So there are two postulates of uncertainty principle. So if this is impossible to find out the momentum of the particle and the positions of the particle at the same times or the simultaneously. And the second postulate was it is impossible to simultaneously describe the absolute accuracy of energy of a particle and the instant of that time that this particle has acquired this energy. Okay, so these are the three principles. So I think up to this is clear. Now, uh, uh, in the next topic, that one will be the Schrodinger's wave equations. So this one will be the up to article number 2.1. This one will be the end of our fourth lectures, and in the next lecture we will learn about the Schrodinger equations, and in the sixth lecture we will learn about the applications of Schrodinger equations. Okay, so try to go through the lecture 4, and hopefully we'll start the fifth lecture from article number 2.2. Thank you.